Hey, it's Canfield. This is BC, Chapter 16, Sequences. We got 12 minutes. Let me see if I can do it. So, if we're trying to write the terms of the sequence, a sequence, so we haven't really looked at anything like this before. It's just a list of numbers. And the way that we can call it is we'll call it like A sub 1, A sub 2, A sub 3, A sub 4, A sub 5. You might remember with polynomials, when we were doing like Taylor and Maclaurin, we would start with A sub 0. These we're going to start with A sub 1 because we're talking about the terms of the sequence. So like if I was talking about A sub 1 here, I would literally plug in 1 and it'd be 4 plus negative 1, so it'd be 3. Then A sub 2, I'd plug in 2 and I'd get 4 plus 1 and get 5. A sub 3, we'd plug in 3, negative 1 to the third is negative 1, so we get 3 again. So we get 5, then we get 3, then we get 5, etc., etc. This is a sequence. With this sequence, you plug in the 1, you get 3 over 2. Plug in the 2, you get 6 over 3. Oh, 6 over 3 simplifies to 2, right? Plug in the 3, you get 9 over 4. Etc., etc., right? So nothing fancy with these. So if we want to look at a recursive formula, this is me writing in cursive because it says cursive. This is I understand this is pretty deep humor. So write the terms of the sequence. So here's what's going on. It says A sub 1 is 3. A sub n is 2 times A sub n minus 1 minus 1. So if I wanted to write this sequence, I'd write 3, comma, for A sub 2, that would be 2 times A sub 1, or the previous term, minus 1. So 2 times the previous term, that'd be 2 times 3, so it'd be 6 minus 1, that'd be 5. If I wanted the next term, it says take 2 times the previous term minus 1. So that'd be 10 minus 1, which is 9. Then that'd be 18 minus 1, which is 17, and so on and so forth. So with this one, it says you start, so it always has to tell you where you're starting from. If you don't know where you're starting from, there's nothing to recur. The reason why it's called recursive is because it's a recurring process. We're doing this thing recursively over and over and over again to the thing that's already there. So this one says, so the thing that's already there, square it, then add 1. So that turns into 1, add 1, you get 2. Square it, then add 1, that's 4 plus 1 is 5. 5 squared is 25 plus 1 is 26. Conveniently, I'm going to stop there because I don't know what 26 squared is. All right, for this one, you start with 22, then you add 2, and then you divide by 2. So it's 24 divided by 2 is 12. That's 12 plus 2 is 14, divided by 2 is 7. Then 9 halves, and then then dot, dot, dot. We use the dot, dot, dot to show that this can go forever. Because we're going to be looking at infinite sequences eventually, and they can go for literally forever. All right, let's keep going. All right, so now we're going to find the rule, and this is a little bit trickier. Now, instead of plugging things in, we're trying to find some kind of rule, and finding explicitly is sometimes easier than finding what we would call the explicit formula. Wait, did I just say explicit both times? Good. Finding it explicitly, such as these, finding the explicit formula is the hard way to do it. Finding a recursive formula is a little bit easier a lot of the time. So sometimes you'll be asked for a recursive rule, sometimes you'll be asked for the explicit rule, but there's no hard and fast way to do it. I just read that off of Stu's page. I just wanted to think if there's anything else I need to say. So with these, it's all a matter of, are we looking for Okay, so if we're trying to find a sub n, we're trying to find an explicit rule then, right? I mean, I want to try to find the explicit rule. So one way to handle this, yeah, there's no way I'm finishing this in 20 minutes. That's fine. We'll do the first part now, and then I'll have time later, I'm sure, to finish it. So one thing to do is to look and see, you know, is it a linear pattern? Is there something else going on? So like on this one, I see that I add 6, then I add 6, then I add 6. So that's linear then. So I know that I'm adding 6 each time. Oh wait, sorry. I'm literally in function, you know, like linear function mode. I need to deal with n. 6n, right? But I know that a sub 1 is 4 and a sub 2 is 10. So like if I plugged in 1 here, I'd get 6. If I plugged in 2 here, I'd get 12. If I plugged in 3 here, I'd get 18. And 6, 12, and 18, those are all 2 more than what we're seeing here. So a sub n would be 6n minus 2. So not the only way to do this, but that's a way to think about this. Let's see, let me figure this one out. Well, this one I see that it's alternating. So that one tells me I'm gonna need some form of like -1 to the n attached to whatever we're doing, if that makes sense. Because as we take -1 to different powers, it switches back from positive to negative and so on, or negative to positive. Let's see, 1, 4, 9, 16. Okay, I add 3, I add 5, I add 7. This is not linear. So something to kind of pay attention to or to look for. You've checked to see if it's linear, it's not. You can check and see for like exponents of things. These all happen to be perfect squares. So instead of saying -1 to the n, I mean, I could just say this is n squared times -1 to the n, right? Because 1 squared, 2 squared, 3 squared, 4 squared. So we could write it like this. We could also just write you know what? I'm just going to leave it like that. That's fine. You can also write -n to the 2n. That would also work. Nope, 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 no, it wouldn't. No, because then our exponent starts changing. Ah! All right, all right. I could say this is, you know, I think this is as nice as I'm gonna get it. There's probably something nicer. I can't think of it right now. All right, this one. Add 1, add 4, add 18. No. So you might see this one and you're like, wait, this isn't an exponent, shoot. Well, I do see it's alternating, so I know there's gonna be some kind of -1 to the n. And this one eludes me a lot of the time. I forget that it's a possibility, but if you remember where we came from, that was where we came from. It might ring a bell. I can actually write this as n factorial times -1 to the n. Right, 1 factorial, 2 factorial, 3 factorial, 4 factorial. Yeah. All right, let's see. What's our next one? Ooh, now we got fractions. So in fraction ones, you can essentially think about the top and bottom separately. Looks like the top is 2, 4, 8, 16, 32. Looks like we're multiplying by 2 each time, but we started out with 2. Oh, we're multiplying by 2 each time. So we'd say this is 2 to the n, right? And then the bottom is 1, 3, 5, 7, 9. These are odd numbers. So a way that you can say odd numbers, there's a few ways that you could write this, but the classic way is to say it's 2n minus 1. So yeah, that's that one, right? 2 to the 5th power is 5. I mean 32. Then 2 times 5 is 10, minus 1 is 9. Cool. This one, so looks like there's a couple of ways we could write the top. We could say it's the nth root of n, or we could say it's n to the 1 over n power all over n plus 1. And then this last one here. Oh, wait. If it was going 1, -1, 1, -1, 1, -1, then I could be like it's -1 to the power of 2 or I mean to n or something like that. But 1, 0, -1, 0, 1, 0. And what? What if I said this was cosine? And then